Cyber-physical systems today have reached a level of extreme complexity. We are building machines with millions of interacting variables, yet we often try to manage them using methods from decades ago. When software, electrical, and mechanical parameters misalign during handoffs, the physical results are devastating. An unsynced limit means the system fractures under pressure. The root cause of these failures usually comes down to a document-centric engineering approach. Teams rely on static PDFs, isolated Excel spreadsheets, and disconnected CAD files to hold the system's logic. In a fragmented ecosystem, updating a parameter in a mechanical model does not automatically trigger an update in the software requirements. The data is siloed, relying entirely on humans to manually track every downstream impact. Attempting to manage thousands of intersecting parameters across static, isolated documents mathematically guarantees structural and operational failure. The human brain simply cannot track that volume of disconnected data. To solve this complexity crisis, the engineering industry established a definitive international standard, ISO IEC IEEE 24641. This standard governs model-based systems and software engineering, or MBSSE. There is a common misconception that adopting this methodology simply means drawing static architecture diagrams on a screen. That approach merely replaces old paper documents with digital pictures. The true objective of the standard's Build Models lifecycle is to establish a mathematically rigorous, fully automated digital thread that connects every stage of development. At the core of this methodology is the concept of the Authoritative Source of Truth, or ASOT. The system model itself serves as the central anchor. The ASOT acts as a computational engine, absorbing disparate engineering artifacts, from text requirements to 2D blueprints, and aligning them into a single synchronized network of data. ISO 24641 officially redefines the system model as an active integrating engine. The first operational phase of the standard is building the models. This requires separating the system design into two distinct architectural layers. First, we have descriptive models. These form the logical blueprint, capturing the overarching system requirements, structural hierarchy, and basic behavioral rules. Beneath that sit the analytical models. These are the discipline-specific quantitative mathematical environments used by specialists to calculate mechanical stress limits and electrical loads. Historically, this is where the process bottlenecks. Descriptive systems models and analytical math models speak entirely different computational languages, making direct communication impossible. ISO 24641 mandates that engineering tools must bridge this gap. They must automate data exchange between domains by establishing strictly defined, explicit interfaces, like the functional mockup interface. By defining these connection points, analytical simulation results route instantly back up into the high-level system architecture to update variables in real time. Establishing this bidirectional, automated interface is the only way to weave a continuous digital thread across multiple engineering disciplines. Once the model is integrated, the next phase is ensuring the design is actually correct. To do this, the standard splits evaluation into two strictly decoupled tracks. The first track is verification. This mathematically answers the internal question, is the model built right? To verify the system, the tool relies on a background metamodel acting as an automated rulebook, continuously enforcing syntax and semantic rules. If a parameter is missing, this check instantly diagnoses deficiencies and flags structural contradictions, catching flaws before human review. The second track is validation, which answers the external question, is the right model built? Validation requires stepping outside the internal code. Engineers map the model's outputs against the operational context to prove that it actually fulfills stakeholder needs in the real world. Verification guarantees the model's internal mathematical integrity, while validation ensures its real-world operational relevance. All of this static modeling, verification, and validation exists merely as preparation for dynamic execution, simulation. Before running a simulation, the environment must seamlessly ingest the central source of truth, along with all specialized analytical data and precise physical boundary conditions. The standard outlines a specific trifecta for analyzing system behavior: virtual, constructive, and live simulation. Virtual simulation serves as the testing ground for human-in-the-loop interactions, where engineers test unpredictable human variables against strict digital rules. This environment analyzes how a pilot or technician will physically interface with the complex machine. Next is constructive simulation. This is the pure computational realm, where AI and math models interact at scale without any direct human input. Constructive environments are designed to mathematically brute force extreme edge cases and failure states. By running millions of scenarios virtually, teams test parameters that would be far too costly or dangerous to attempt physically. Finally, live simulation provides the ultimate reality check, utilizing physical prototypes tested in actual operational environments to gather empirical evaluation data. This data is fed directly back into the digital twin, correcting the initial math and tightening the accuracy of the models. This multidimensional matrix closes the engineering loop, transforming theoretical architectures into mathematically proven, predictive behavior. The entire data collection, modeling, and simulation pipeline exists for one core purpose: eradicating subjective, opinion-based design decisions. Engineering always involves trade-offs. We use simulation data to evaluate competing architectural alternatives against conflicting requirements, such as cost limitations, maximum weight, and power consumption. ISO 24641 dictates that engineering tools must capture these specific decision criteria directly. They must be embedded within the model as rigid mathematical constraints, rather than loose text guidelines. This decision dashboard aggregates the massive simulation matrix, automatically weighing design alternatives against hard constraints to generate an objective stakeholder assessment. The tool then highlights the mathematically optimal solution, allowing the team to confidently lock in the final architecture. This framework anchors complex systems design in rigorous algorithmic proof. This brings us to the final and often most ignored step in the standard: building the rationale. Once a design decision is made, the logic behind why it was chosen must not be lost to human memory. It must be permanently inscribed into the system's history. The tool embeds this rationale directly into the model's traceability records, linking the choice to the exact criteria. Embedding this logic enables true knowledge reuse. Future engineers can instantly track a design's lineage, avoiding expensive mistakes when updating the system years later. This is the fully realized power of the ISO 24641 pipeline. You build the descriptive and analytical structures, verify and validate their integrity, simulate their behavior across multiple dimensions, and systematically execute optimal design decisions. True MBSSE orchestrates an active, computable engine of total system knowledge.